Hey, welcome everybody. This is VLSM. We're going to get into the concept now that extends the subnetting concept a little bit further. Here's what we know. We understand that we might have a network which is something like a 172.16.0.0, and we might say we'll assign a /16 to that, meaning we're going running from 172.16.0.0 to 255, a block of 65,536 addresses, a lot of IPs, a lot of space in there. But we might have something like this, a router interface that's going to come off to networks of 170 computers here, maybe another one of 35 computers here. And what we would have done up to this point is we found something to accommodate this 170. We've created that division, started with that network. We'll say something like, all right, let's put a /24 there. That will give us 254 unique addresses to assign to host, networks of 256. So we're good to go. And then we'd come over here and go, all right, let's keep things nice and clean. We're going to give you a /24, and you can accommodate 254 unique devices over here. From here to here, there's a lot more wasted space than you might see here. So what VLSM does, variable length subnetting mask, gives us the ability to take these fixed length subnet masks that we've established up to this point and say, you know what, that doesn't quite fit for what we need to do. We actually can accommodate this guy much smaller. We could take something like a /26 who might have 62 addresses available to host. Remember, networks of 64 minus your 2 that you can't use, your net ID, your broadcast, to get you down to 62. 62 to 35, look at that. We still got some space to work with, but we have not wasted as we have when this was a /24. Therefore, VLSM will allow us to actually conserve IPs better than fixed length subnetting masks. That is the whole purpose behind doing it. Let me show you a chart that will help you guys out as you move through this process. And let me also walk through a couple examples with you of how we'll make this work. Now, something similar to this, if you were to go to Google Images and search for VLSM chart, you'll come up with some similar results, excuse me. And basically what we do here, this guy gives us our starting range for our smallest of networks, this over here. And it tells us possible options for where we could start networks depending on what size we chose. Now, you start looking from here, and this tells you where you could start if you happen to assign a /25 of 126 hosts. You can start that network at 0. You can start a network at 128. Now, if we went to a /26 and we borrow 2 subnet bits, hosts would be 62 in size. We would start a network of 0, 64, 128, 192. We get 4 blocks in here. /27, 3 bits, 30 hosts, and look what we're doing. All right, now remember these divisions and breakups, if it's a /27, that's going to be the same thing as a /19. We're dealing with more hosts. 30 is not the correct number at that point in time, but these divisions and where networks start does not change. Now, if we went with a /28, borrowed 4 bits, 14 hosts, you can see where they start. So without reading off the whole chart to you, I don't want to bore you guys, but something like this becomes very useful as you want to get used to where these divisions happen. You want to get used to the hosts you can accommodate with different size networks. These patterns will start to make sense, and the more you practice this, the more you do it, the better this becomes. It's like learning a multiplication chart. The more you practice it, it just kind of sticks, and you'll be able to spit them out without even really thinking about it. So the best that we can do to accommodate host is a /30 where we will get 2 hosts out of it. You don't want to go any further. /31, you have 2 addresses, but out of those 2 addresses you have a net ID, you have a broadcast, and you're done. /30 gets you blocks of 4, 2 addresses that we can actually assign. That becomes good if we have, say, a router here connecting to a router here, and then we have a network here, and we have a network here. Well, here in the middle, we might just want to put a /30. Could you imagine if these guys were 100 and let's say 24 hosts over here, and this guy was 192 hosts over here, and we said, whoa, okay, looking at that, we're actually going to have to assign a block of /24 to accommodate this. And we'll just keep it clean. We'll put a /24 over here, and well, I guess we'll do a /24 up here. So 254 available addresses, and you have 2 interfaces that exist in there. Lots and lots of waste. VLSM is going to create a solution around that, but there's one major thing that you must keep in mind. You are going to want to start accommodating your largest networks first, and then work your way to your smallest networks. And there's a fundamental reason why. Larger networks have less options on where they can start. A /25 or a /17 or a /9 can begin at a .0 and a .128. As you chop up the networks and borrow bits and move this way, your options for where you can start networks greatly increase. So you are most likely to find the ability to accommodate these sizes here much easier than accommodating these sizes here. So what happens is we need to accommodate a /26, we need to accommodate a /28, and we need a /29. So here's what we do. Starting with this guy here, we take that first and we say, all right, let's accommodate him first, /0, just because I like that network the best. Where these guys are located, my buddy's there, so I'm going to make sure I get him divided up first and he's good to go. Okay. Then you come over here and you go, well, where can we start next? We have a .64. Well, let's accommodate this guy next. And then you say, all right, let's just start with this /28 as our 3rd network here. And you go, oh, wow, okay, so my option is /80. That's where I have to start him. What's happening here? /70, this another /29, this .72 to .79. What can you do with them? That's dead space that you've now created, because by starting him here, the next network, if you went here for /28, the next network would have to start at a 80. And let's say you finished there, you went all the way up to a .95. As we know, 96 is the start of the next. So you come over here and you go .96. Oh, okay, well, I'll have to start at .128. Well, what happens with all of this space? You got 96 all the way down to 127. Where's that? Okay, that becomes a problem, because now this becomes dead space right in the middle of your block. So as much as you're using VLSM to accommodate and conserve addresses, you're now creating gaps in there, which means you're actually killing blocks as well. Okay, same thing would have happened right here. This guy would have been out, and that would have been a problem. So you got to understand, we have to go with our largest network first, and then we're going to accommodate our smallest networks. In this same scenario, if we were to start with our /25 and get him out of the way, and we say, here we go, let's grab you, we got you accommodated, and then we say, yeah, we need a /26 too, so let's work our way here. Okay, look at that. Starting nice and clean. /28, well, let's get you out the way. We'll do a .92. Check this out, /29. Look, he's available at the very next spot. So nice and clean, we have accommodated 1, 2, 3, 4 networks without any wasted space in there. We would have a spot where we stop, and then we would understand that now we have area that we could continue to work with if we have other networks to accommodate. Everything here, those are still good blocks. So as you can see, starting with your large networks, working your way down to your smaller networks, you're going to have much more success at saving space. Alright guys, so here goes a practical implementation of VLSM. Now remember, initially what we would do is we would find our largest guy here. We would go, well, we can accommodate that with a /25. We'll take that /25, we'll apply it here, we'll apply it here, we'll apply it here, do that here, do that here. And what happens, remember, a /25 is 2 of these together equal 1/24. Okay, so you end up with 3 /24s that you'd have to implement. This guy here and this guy here as well, with 2 /25s. 3 /24s, and they don't even divide with 3 /24s. So you'd actually have to increase that. Instead of a /23, you'd have to go one step further and make a /22 to accommodate all these if this is the route you tried to go, to divide them up that much. Okay, that becomes a lot of wastefulness. So let's get that off the screen and let's look at this problem a little bit differently. Okay, from a VLSM standpoint, let's start looking at our chart and see how we're actually going to divide these guys up and what we will need. With a /25, we can accommodate 126 hosts. Okay, /26, we can do 62, /27, /30. Let's knock out our largest network first, since that is the route we want to go. We're going to /25 on this guy. Okay, let's take a look at what we're going to do next. We have a 50 and a 40. Those are our next 2 largest. Well, 30 is too few. 62 works for us. That is a /26. So let's come back over here and let's grab a /26 here, a /26 here. 10 more to go. We got one here, /28, that accommodates 14 hosts. So let's grab that. And 2 and 2. See what we're going to do there. That's where we get to this /30 guy up here. Okay, /30 comes in handy a lot when we're dealing with point-to-points, as we are here. We've got one router interface to another router interface. Okay, so we're going to take those guys. We're going to do a /30 for this guy. We'll do a /30 for this guy. And then let's see how far we've actually extended. Remember, initially, we were going to break this guy out to a /22 to be able to accommodate all of the hosts, just because of the divisions that we were creating of /24s. Instead, we started with a 192, 168, 10. We could turn around from there and say, all right, that guy's going to extend all the way to a 127, meaning that this guy would start at 128. He is going to extend from a /26, 64 addresses. So from there, it's going to run to a .191. So let's bring that up over here. We're now at a 192. We have not left this right here. Okay, /26, that's going to run us from there to 255. Okay, at that point in time, we have finished this first block. 192, 168, 20. we grab a slash 28 there. Slash 28 extends 16, which means he's going to go to 215. That guy is him. And 2 slash 30s. So from 16, we would run to, we're at a dot 16. We can go from 16 to 20 and 20 to 23. And that's where we would end. Let's get this back out the way. And we would end with 192, 168 to 16 to 219, and then 20 to 23. And we have now confined what was going to take a slash 22, and we have chopped it much smaller without wasting the addresses. So that's where this comes into play. Here's something I don't want you to do. This is a common mistake you can make with this. Don't simply take this hosts and these hosts and these hosts here, here, and here, and add them up and say, hey, 105, 155, 195, 205, 207, 209. That's all I need is 209 hosts. So that means all I need is 1/24, and I can divide them from there. That doesn't work because remember, these guys have to divide into certain predetermined blocks depending on what bits you have borrowed. Therefore, as we saw with our example, this guy does not fit into a /24. He actually extends. What you might actually have to do is to create a /23, which means he would run somewhere from 192, 168, 0, 0. Remember, we'd have to start in that 0 block and extend him to 1.255. Okay? It still has some waste at the end. As we saw with our example, we would extend somewhere into 1.24, I think, was our last usable that we would have seen from this example here, the way we have to divide them up. So from 24 up to 255, but that could be room for expansion. Okay. It does not get as wasteful as a /22, which would run from 0, 0 to 3, 255. That would create a lot more waste. So just keep those things in mind. Let's look at one more example, and let's do a class A, something much larger. Let's say we end up with something like this. This guy's going to be a doozy. So we have a 10.0.0.0 network, a /8, and we need to create, from a VLSM standpoint, something that's going to accommodate 1 million hosts, 550,000, 250,000, and then 200 hosts. I'm going to introduce the IPv4 cheat sheet here just to get these numbers quickly for you guys, okay? That is a link that you can find. I'll post it with this video in the description area so you can get to a video on how to create this same cheat sheet. And all it will simply do is help you create these divisions right here much quicker using Cedar. Let me show you the cheat sheet and what it looks like. I'll give you a real quick overview. So because we're dealing with a /8, our concerns here that we're going to be looking at, these bit values, these would be the bit values in our second octet, our /9 through /16 area. Okay? If we enable bits, that becomes the additive. If we enable these bits in that second octet, this becomes the additive of when networks get added to one another, where they start. As example, if we enable that first bit, as we've seen with our previous example, /25, our next network starts at .128. Well, if we do it in a /9 position, then that means we're running a network from 10.0.0.0 to 10.127, 255. The next network is this additive of 10.128.0.0. Okay? Big numbers, quick overview of this. Let's get it to make sense. Now, our additives also help us determine our mask. Depending on how many bits we enable in that second octet, pay attention to where we are. We're starting with an 8. We're talking about this column. That second octet, that mask value, subnet mask value, instead of being 255.0.0.0, becomes, if we enable this bit, it becomes 255.128.0.0. If we enable the first 2 bits, then it becomes 255.192.0.0. That will tell us that with that mask value, that's how our networks add. Subnets, well, if we create a division here, then that's how many subnets are created. We can do 2 networks. If we have a /9, we can do a 10.0.0.0 network and a 10.128.0.0 network. Here is your bit patterns that you can now enable: /9, 10, 11, 12, 13, 14, 15, up to a 16 where you have 255. Okay? Now, here is the column that will be of the most use for what we're doing. If we take a /9, instead of having this network, which has 16.77 million hosts in it, we have 2 subnetworks of 8.388 million in each one. If we did a /10, he will create 4 networks of 4,194,302. So you can see how this will quickly get these kind of values for us. So let's start breaking this network down and let's see how it's going to work. So right off the bat, what we see here is we're starting with a 10.0.0.0/8, meaning that we have this entire range to work with. We need to squeeze these guys in there, and we need to see how we can make them fit. Our very first network we're going to use, this guy here, he's going to start at 10.0.0.0. What seeder value do we have to give him to accommodate these hosts? Well, if we go right down this A column, if we go to this point right here, we will create a network that holds 1,048,574 hosts. We need 1 million hosts. We're going to come across, we're dealing with a /12. There's our mask value of that octet. We're going to go /12. We will also need to know this 16. Because what that additive tells us is where the next network is going to start. We will have 10.16.0.0. Why did I put 16 here? /12. We're dealing in this second octet. When we did a /12 here, 1, 2, 3, 4, 5, 6, 7, 8. That's your .8 up here. 9, 10, 11, 12. And then we zeroed out all the way down. So that is what we're working with, a /12. If we have a /12, we have an additive of 16, which means our next network started at 16. Why did we do that? Well, to accommodate these hosts, to accommodate this million hosts, this needs to run from there, 10.0.0.0 to 10.15, 255, 255. Okay? That's one network done and out the way. We need another 1 million hosts accommodated for. We just did the math. We just figured it out. 1 million hosts get accommodated at a /12. So why don't we just repeat that process over here and create another /12. Okay, if we create another /12, what's going to happen to our hosts? We are going to run, remember our additive, 16. The next network is going to be 1032.00, so we're going to run from here to 1031, 255, 255. We are accommodating our largest networks first. They're both done. They're out the way by using 2 /12s, and out of our original 16 million hosts, we've taken 2 million out of it by dividing our networks down. Let's see what we need this time. 500,000 hosts. So we'll move right down this line again, and we'll see that we can accommodate 550,000 hosts. Now, /13 is not quite going to do it. That's 524,000. We're actually going to have to do one more /12 to accommodate. I don't think that's a problem. I like the /12s. We have some experience with them right now. Let's get that out the way. Remember, additives of 16 for what we've used. So to accommodate this, we're going 12 again. 32 plus 16, 1048.00 is our next network, which means that we ran down to 1047, 255, 255. 3 million hosts and some change, so we're a little bit over that at this point in time. But now we've accommodated another network. We need 250,000 and 200,000. Let's see if this is going to use the same subnet mask for both of these. 250 and 200. Right here at a /14, we're going to accommodate 262,000 hosts. If we go to a /15, we've gone too far. If we go to a /13, that's too much wasted space. That, from a VLSM standpoint, that's going to help us conserve our addresses. /14, and we're going to make 2 of them. We need to get some information real quick before we start moving to the other side and writing this up. /14 is going to get us our 262,000 hosts. We need to understand that our mask value becomes 255, 252, and we need to understand networks add every 4. We have enabled 6 bits, so we went from a /8 to a /14. So let's start breaking this down. Now recall, /14 gave us an additive of 4, so we're going, our next network is going to be 1052.00. Now let's finish this network. We create that line, 1051, 255, 255, and where's he going to extend to? From 1052, the next one will be 1056, so we're going to go 1055, 255, 255. So variable length subnetting mask dealing with these extremely large networks, that's how we can divide this thing and break it up, and that's kind of what we're going to end up with there. That's a challenge to do by hand. You can do it by hand. Your hosts always double as you move, as your bits. This happens to be your subnet mask. Okay, remember from our previous nugget that as we borrow mask bits this way, networks double, and as we borrow mask bits, or as we kind of return them back, the zeros we have, each bit over that we move, we double hosts. Host times 2. Networks times 2, host times 2 as we use each bit. Okay? So that's a breakdown of VLSM. That's the concept behind it and how it works. It will take some practice for you to get used to doing. I suggest that you jump to the challenge me, and I gave you a little problem in there for you to try to work through. I don't think it's difficult. I think you're going to get it. It's a Class C. I just wanted an example of a Class A, because if you can see an A, you should see a B and work your way through it. Again, you will basically start with your beginning range, whatever your CEDAR value happens to be. Largest network first. Find your division. Find out where the next network starts. And then now you have your previous network info. Again, where's the next network start to accommodate the host? We find a CEDAR value. Boom. You're going to build right down a list like this. That's Practical VLSM. This is James Graves. I'll see you in the next video.